Today, I'm going to give you guys an overview over some of the activities that we're doing related to CCS. And normally I would ask the audience to raise their hand if you heard about CCS, but this is a digital event, so it's kind of hard to do that. But I believe most of you have heard about CCS, carbon capture and storage, and also about the activities that are ongoing here in the outside, in the west coast of Norway. And I'm going to also touch upon hydrogen storage underground, which is a fairly recent activity for me, whereas CCS has been an ongoing theme for quite some years. And I'm going to try to use a recent laboratory development as a framework for my discussion today. And this is the fluid flower. So the fluid flower concept was developed here through a interdisciplinary collaboration between the physics, mathematics, and geology department, where we actually tried to combine CCS research and dissemination. So we believe it's very important to actually show people where and how and why CO2 is stored underground. Some people believe that we will store it in the water column in the ocean, but actually we will store it up to 3 kilometers underneath the seabed. And what you see here is actually a picture of this new rig that we built. It's 3 meters wide and 2 meters high, and we can build a reservoir, which is the location in the subsurface where we will store the CO2. This is currently located here at the Department of Physics and Technology, and right now we are running some, well, it's not secret, but I will come back to it. So that's why it's built in a black box at the moment. So I will come back to why that's important. So it's not only sort of pretty to look at, but there's actual research going on. And here you can see some of the instrumentation behind the scenes. So in the picture to the right, we're injecting and producing liquids. We're measuring the pressure and so on. So it's a big apparatus, which is highly active at the moment. So this slide sort of sums up a lot of the activity on CCS that I will talk about today. I will then go through some of the details. So as I mentioned, it's an interdisciplinary CCS research and dissemination across 3 departments at UIB. And we started this, I would say, well, initially in the autumn of 2020. And as you can see, we have a lot of international collaboration already ongoing on this. So the picture that you see is an actual picture from the rig. You can also go into this website, and I can post in the chat later. And you see porous media, which is relevant to the reservoirs that you'll have on the Norwegian continental shelf. Now, I'm not a geologist, and I couldn't see any geologists in the crowd here, but basically we have relevant geology captured in this rig. And the colors is actually after a well and tracer test, something that they will typically do to gain information about the flow properties of the reservoir. And we also done that here in this experimental setup. I'm going to talk about 3 projects today. The international benchmark study, the PoroTwin project, and also a project called Nonuniqueness in multi-phase flow. And I have some detailed slide on this. For the international benchmark study, what we're actually trying to do is to have a full physics validation of simulation capabilities within the international porous media community, represented by these research group at these institutions here: MIT, Imperial, Stanford, Texas, Los Alamos, and so on. It's actually quite an international study, also with 2 participants from Australia and Europe and so on. That's a double-blinded study. They cannot see what we're doing in the lab, and we will not see how they perform on their modeling. And it's ongoing, and it will be finalized in March of next year. And then we have, because it's a double-blind study, I can actually not show you any CO2 being stored in the large rig, because potentially some of you, and this is also being recorded, some of the participants could see this presentation and actually get hints and help in their modeling efforts. So, but I will show you some other CO2 injections from another geometry very soon. I will just go through this. The PoroTwin, here we actually develop a digital twin of the physical flow rig with real-time integration, simulation and control over the experimental parameters. And then the non-uniqueness project actually will evaluate when we do reproduce, well, how good are we at reproducing ourselves in the lab? So we will run identical experiments several times and then look at how much they overlap for each time. There is a degree of stochastic variability in flow in porous media. We would like to quantify this. Here I have a video over a CO2 injection into a reservoir, and you can see that the colors are changing as the CO2 is injected. This is pure CO2 being injected, and very much like the Northern Lights project. Actually, the geometry that you see here is inspired by the Northern Lights storage site. This is in the lab, so it goes quite quickly compared to what they would do in the field. But what's interesting here is that all the physics and chemistry that you have in the reservoir would also occur here. So if you haven't seen CO2 being stored before, you're currently seeing it. So we're injecting CO2 into a water-filled reservoir. It displaces the water and it fills up the reservoir. It also changes color here. I can come back to why that's important, but we have designed this experiment or this setup to change its color when the CO2 mixes with water and makes basically carbonated water, which some of you might be drinking right now. So yellow color in this movie is carbonated water, which is actually one of the storage mechanisms for CCS. I will skip this because we don't have time to go through all of it today in this short presentation. But here you will see the distribution of CO2 and carbonated water within the reservoir after we stopped injecting. And probably you don't know, you haven't worked on reservoir physics for the last 20 years, so I will go very quickly through what we actually see here. So again, we have the same physics and the same storage mechanisms in our lab experiment as we actually have in the Northern Lights reservoir. And we can zoom in here and see the droplets or gas bubbles being trapped within the porous media, which you can also see the sand grains here. We have large grains at the bottom and then finer sand on top. This is how a sandstone looks like, although that's they're more compressed when they're 3 kilometers underground. So here you see this trapping mechanism called residually trapped gas bubbles, and you can see the bubbles are being trapped here. We also have a trap of free gas, which is actually, in this case, trapped under a tighter sand that has a lower flow capacity than the sand below here. So then the CO2 gets trapped underneath this low flow capacity sand. We also have something called sealing barriers or structural trapping. So this is basically a lid over the reservoir that keeps the CO2 contained. And then finally, we have the diffusive transport of CO2. Then diffusion is active in the experiment and also at the field scale. So we have all these trapping mechanisms active in the experiment and the field. And one of the main points here actually, as the storage security in a way actually increases over time, because the yellow phase here that you see is a little bit denser than the water originally in the reservoir. So it will move towards the bottom. So as time progresses, and this is true also for storage sites, the leakage potential go down and it gets more and more secure, if you like. Then I will just very briefly talk about this. What we see here is comparing two runs in another geometry. This looks kind of like a dragon, if you like, which is red, and that's where the two experiments are overlapping. And then we have some gray areas here, and that's where one of the experiments diverge from the other. So this is an example of non-uniqueness, where we actually see that even though we did everything identical for two runs, they do not behave identically. And that's something that we need to account for in our modeling efforts. But first we need to understand it in the lab. So we have a PhD working on this right now. Here's a sneak peek of the benchmark study. We have 10 modeling groups worldwide working on this. And because I cannot show you any results from the actual CO2 injection, but I can show you some results from the tracer test, where we actually injected water of different colors into the reservoir, and we provide that to the modeling group, and they can use that data to tune their model. And on the right, we see an experimental result. You don't have to understand all of this, but you can see the different colors. And then you see this whiter color here being distributed in the reservoir. And then at the math department here at UIB, they did a model of this, and you can pretty much see that they did a great job in capturing the distribution of this tracer. Although the colors are a little bit inverted here, you see that this blob up here looks very much like this blob here, and then the distribution down here very much aligns with what you see down here. So this was also done blind, so they didn't see, they don't know anything else than this picture, but they were able to simulate it in a very good way. So it looks like the benchmark study is on track, to put it like this. I also want to touch upon this PoraTwin project. All of these projects so far have one thing in common, and that's the fluid flower rig. Here we actually develop a digital twin that are gonna, through a hybrid analysis and modeling effort, look at why the model, here is a slightly older picture of this modeling effort, does not perfectly match the experiment. So there is a discrepancy between the model and the real world, so to speak, which is mostly the case. And the reason for this is unresolved physics or chemistry, if you like, in the model. So this project is going to target this unresolved physics in the model and try to help the modeling community in a way, or the work processes, to be able to have a higher confidence in the modeling efforts. And then we have a, let's see here, if this, yeah, okay. So related to this, we also have started a project now this fall, which are looking at storing hydrogen. Most of you probably know about hydrogen. We talked a little bit about blue hydrogen before we started. So this project has the long title of Hydrogen Storage in Subsurface Porous Media, but it has the short title called HYPE. This was awarded by the Norwegian Research Council. And the idea is that if you have hydrogen, surplus hydrogen, let's say from energy, or sorry, electricity production, or if you have vast amounts of blue hydrogen, you need to be able to store those volumes. And you have a range of storage technologies available, and this would be sort of on the far end of the spectrum, both in terms of size, because you can then utilize the subsurface with well, millions of cubic meters of storage potential, but it's also going to be slow, sort of seasonal storage of hydrogen. So you then temporarily store your hydrogen in the subsurface, and then you produce it back up when you need it. You have to plan ahead, though, because these volumes that you get up are vast. We have 3 work packages. We're zooming into the rock and looking at hydrogen methane flow, trapping, and solubility. The reason why we have methane here is that candidates for storing hydrogen in the subsurface is many, but I think the most sort of readily available one would be in a depleted gas reservoir, where you have produced the natural gas that you can and want to produce, and then you can convert this into a hydrogen storage unit. When you inject the hydrogen into these reservoirs, you're going to see an increased bacterial growth due to the indigenous microbes that are present in the subsurface, and they can both reduce the volume available for hydrogen and also reduce the flow capacity of the reservoir, and they can also convert hydrogen and CO2 into methane. There's actually a project looking into working this to make synthetic methane, actually, but that's not part of this project. And then work package. So we have a work package looking into this, and then the work package 3 is how to couple this and actually come up with a modeling tool that incorporates this knowledge, which the reason I think this is exciting is that there's very limited information about this in the open literature, in the order of 30 to 40 papers worldwide on this topic, but obviously it's a relevant topic in this upscaling of renewables. So it's a 5-year project that we start now, and I'm in charge of making this a success. And then I would like to just briefly end just a little pitch about a continuing learning course that we have on CCUS, where we talk about hydrogen, we talk about capturing technologies and so on. It's a very popular course. We currently have, I believe it's 3 parallel courses running, and I think the number is exceeding 400 applicants on this, and here is the group that sort of holds this. So most of these are here at our Department of Physics and Technology. And I think that's it.